All right, guys, this is the second time I'm recording this. I didn't press play on my last one, so hopefully this one works out. Yeah, so today we're going to be learning about quaternions. They're like forms of measuring rotation in 3D space, and it's really important for this robot that we're making because we're going to be handling like rotating arms and stuff. I felt like that was pretty explicit, so I'll shut up now. We're going to be watching this video called How Quaternions Produce 3D Rotation by Penguin Maths, so let's get into it. Alrighty. This is cinematic. I love it. I love it already. Look at that guy. It's me. It's
If
my
you
face.
like math, you may have
I
heard
hate
of
math. Fuck you.
quaternions.
Sorry.
You might even know that they're often used as a way of representing rotation in 3D graphics, like video games.
Mm-hmm.
But why
Like Minecraft.
quaternions instead of something simpler, like Euler angles? And how quaternions? How does
So just for context, Euler angles are is another way of forming 3D space where you take an object and you rotate it on its y-axis, and then x-axis, and then z-axis, or whatever order it is. But it creates this problem when you have two of the same axes. It's hard you can't distinguish, its orientation if they both line up. So this is why quaternions are used in computer science and gaming specifically.
how does something like that produce rotation?
You're right.
Quaternions?
Oh my gosh, it's the guy. It's for
I once met someone.
It's the penguin guy from the memes. Wait. Pause. I don't even know what the show's called. Claymation penguin dude. Okay. Yeah, it's this guy with his family. Yeah. I don't know where this is from. Yeah, what is this from? Pingu. It's Pingu. Am I saying that wrong? I'm so sorry for the Pingu fans out there. I'm uncultured. That's what it is.
Someone who knew someone that said they're super confusing and to stay away from them.
Yeah.
They can be
you're right.
confusing if you're unfamiliar with them, but that's true of everything.
All right. But before you start talking like a nerd, can you explain what quaternions
Before you stop talking like a nerd. Yeah. You loser.
even are?
Sure. Quaternions are a four-dimensional extension of the complex numbers. Complex numbers are of the form a plus bi. Quaternions are of the form a plus bi plus cj plus dk, where a, b, c, d are real numbers, and I, j, and k are the fundamental quaternion units.
The fundamental quaternion units.
So complex numbers can be thought
Sorry, I tried doing like an old, 1800s voice, but it just kind of came out Indian. That's my bad.
of quaternions which have c and d equal to 0, just like real numbers can be thought of complex numbers with b equal to 0. Remember how multiplying two unit complex numbers results in a pure rotation? In other words, multiplying two complex numbers with magnitude 1 results in a new complex number with magnitude 1.
Ah, I see.
Results in a new
Interesting. Yeah, that makes sense.
complex number with magnitude 1.
Ah, I see. So
I see. Multiplying
two unit quaternions results in another unit quaternion. Then it's a rotation. That's easy.
Okay,
Well-
that makes sense. All right, so if you have two vectors and their magnitude is 1, so it's a unit vector, when you multiply them, the magnitude of the vector doesn't change because you're multiplying 1 by 1, but the angle changes, so it creates an angle. Oh my goodness. So
You're
smart.
partly right. It
Oh.
does
You just proved me wrong in like 5 seconds.
result in another unit quaternion.
Sorry,
But
let's play that
you're
again.
partly right. It does result in another unit quaternion. But we are interested in making a 3D rotation. Quaternions are four-dimensional, so it's not as simple as that.
Gotcha, okay.
Let's take a look at the
makes sense.
multiplication rules of quaternions. These rules don't make it immediately obvious what happens rotation-wise when two quaternions are multiplied. Note, though, that any two fundamental quaternion units being multiplied together do not commute. One is the negation of the other. But
Okay.
any fundamental quaternion unit multiplying itself or a real number does commute. Keep this in the back of your mind. It will be important later.
It's back there. Don't worry,
Consider
Steve.
this diagram.
I don't know why your name is Steve.
Look familiar?
Maybe the Minecraft.
It's the same stereographic projection that 3 Blue 1 Brown used in his video on quaternions. If you haven't seen it, I highly recommend watching it and playing with quaternions on his and Ben Eater's interactive website,
I've heard
as
about
it
this.
will
It's
help
actually
you
really cool.
understand how to interpret this projection.
Yeah, I watched
I'll
this
place
video
a link
too
to those
earlier.
in the description. Now, imagine left multiplying 1 minus 1 and each of the fundamental quaternion units by I.
Okay.
It rotates the circle passing through 1 and I,
Wait,
as
I need
well
to see
as
that again. What did you just do?
fundamental
You just
quaternion
did freaking
left
jujitsu right
multiplying
here.
1 minus 1 and each of the fundamental quaternion units by I. It rotates the circle passing through 1 and I, as well as rotating the perpendicular circle that passes through J and K, such that 1 gets mapped to I, and J gets mapped to K.
Let's say that again. I'm so sorry. I don't get this still.
1 minus 1.
Okay, so we have this guy. It's 1. And I, J, and K are the axes for the imaginary numbers. So what are we doing? We're multiplying by I. When we multiply by
each of
I,
the fundamental quaternion units by I.
okay, when we do that, everything's going to shift because now I times 1 becomes I where it originally was, and then I times negative I becomes 1, and it makes that shift. That makes sense. That makes sense.
It rotates the circle passing through 1 and I, as well as rotating the perpendicular circle that passes through J and K.
Does it? Seems like it's the same. Maybe I'm just not picking up on something. Let's keep watching. Just keep watching.
As well as rotating the perpendicular circle that passes through J and K, such that 1 gets mapped to I,
Okay.
and J gets mapped to K.
Does it though?
Let's
pause. So let's see that. Yeah, maybe I wasn't paying attention.
by I.
So I times J becomes K because of the multiplication rules that we see at the top left corner. Okay. Yeah, I see it. Okay, so it does make sense because everything did shift. So it shifted from negative I to I, shifted 1 unit of I, and then J rotated 90 degrees. Or I guess J is mapped to K now. Ha! Got it.
Rotates the circle passing through 1 and I, as well as rotating the perpendicular circle that passes through J and K, such that 1 gets mapped to I,
Yeah.
and
All right.
J
Come on.
gets
I already got
mapped to
this.
K.
It took me like 5 more minutes than you did, but hey.
Let's watch that again.
Oh, let's
this
watch it
time
again.
only focusing on what happens to 1 and J. First, left multiply both by I times 1 is just equal to I.
Oh, he's
And I
explaining
times J, according to the definition of...
Guys, this is a problem I have. I just pause it and then I'm confused and I don't bother to keep watching because I just want to like figure it out in the moment. But you literally just explained it to my face, man. So I'm gonna try to just let the video play and write down my questions. Maybe writing down my questions might be easier. Let's try that.
Of quaternion multiplication equals K.
Wait a minute. How do you know these multiplication rules are true? You basically pulled them out of a hat.
Yeah, you
It's
idiot.
because this is the
It's
definition
like, wait. All right, I know they wrote in the script, but this penguin's really skeptical.
of quaternion multiplication. It's not that we know it's true, it's that we're defining it to be true. Then
Okay.
we can see what logical consequences follow from this definition. William Hamilton, the guy who invented quaternions, chose this definition because it has some nice algebraic properties. Now, let's see what happens when we left multiply by minus I.
It should go backwards and then
That's
rotate
not too
it
surprising.
clockwise.
It just rotates the same two circles in the
Yep.
opposite direction than positive I did. Again, focusing on 1 and J, we see that 1 gets mapped to minus I and J gets mapped to minus K. But now, let's try something a little crazy. What if we right multiply?
No
by
way,
minus
bro.
I?
That's nuts. You're insane, dude.
Well, remember, right multiplying only rotates the opposite direction than left multiplying when you're multiplying two different fundamental quaternion units. So the circle that passes through 1 and I will be unaffected by switching to right multiplication, but the circle passing through J and K will now rotate the opposite direction. So now 1 gets mapped to minus I, still, and J gets mapped to positive K. But wait, what will happen if we first right multiply by minus I, then left multiply the result of that by I, so that our equation looks like I times V times minus I, where v is some unit quaternion from the
So you just
diagram.
need one.
Gosh, I don't know.
So I squares
Wait,
negative 1.
I think I get
Negative
it.
negative 1 is 1.
The two circles spinning in different directions will cancel out.
Yes, the rotation of the
I should just
circle
teach the
passing
class
through
at this
1
point. I'm
and
just so
I
cracked.
cancelled out, while the rotation of the circle passing through j and k has doubled. We have effectively created a rotation only about the I-axis.
Hooray! I did it! Do I get a prize?
You earned it. We can generalize this to create a pure rotation about...
So yeah, because last time, I guess when you're multiplying, or when you're left multiplying by I, the axis moved backwards. And when you're right multiplying by negative I, it moves forward. So they cancel out, and all you're left with is the rotation, yeah.
About any unit
That's not what I said before, but I'm going to pretend it was, so.
vector that is a combination of I, j, and k. First, some terminology. The vector part of a quaternion is the component that lies in the ijk space, whereas the real part is the component lying on the real axis. A quaternion whose real part is 0 is called a pure quaternion. The conjugate of a quaternion q is denoted q bar, and it's simply q with the vector part negated. So
Let's read that again. The conjugate of quaternion q denoted q hat is q with the vector part negated. Oh, negated. I forgot what negated mean. I'm so stupid. Okay, got it. Done.
q is denoted q bar, and it's simply q with the vector part negated. So to describe the general form of what we just did a moment ago, we can write q v q conjugate, where v is a pure quaternion, whose vector part is the 3D vector that we want to rotate. And q somehow describes the angle and axis to rotate about. And v does not need to be a unit quaternion, only a pure quaternion, so don't mix those two up. In the example we just did, v equals j and q equals I. Performing the multiplication, we saw that v rotates 180 degrees about the I-axis. So the obvious question now is, how do we pick q to perform our desired rotation about any axis and any angle?
Guys, I have to go to an appointment right now. I'll be right back in like an hour, so we'll learn more about these in a sec. Did you miss me? No, you definitely didn't. You definitely have no feeling at all for watching a video on quaternions, dude. You probably run on straight binary. I don't even know. All right, let's get back into it. Where are we at? Oh, yeah, we're talking about this QVQ hat, where Q is, I don't know what it's called, but it's like the first rotation. V is just the, what is it called? Just the vector parts times the negated, because Q hat means negation, right? Let's see.
I think it was the axis. So the obvious question now is, how do we pick q to perform our desired rotation
Oh, that's right. That's
about
right. We're
any
back. We're back.
axis and any angle? I think it will be helpful to find a way to visualize the 4D unit hypersphere, since
Okay.
that's where the unit quaternions live. Any suggestions? I think you're 1 dimension too low.
We look
Let's
stripping.
try this. It looks like a normal sphere, except the red region in the middle is actually a 3D space, the IJK space, which is squished down into a flat circle. The axis perpendicular to that is the real axis. Just don't forget the red region is actually 3D, and the flat appearance is just an artifact of the schematic.
Okay, I can do that.
So this is a unit quaternion with a vector part and a real part.
Oh, I forgot to turn on my light. Let's put the light back. Orange light. Then you said, "Let there be light." Oh, yeah. That's going right there. We're back. We're back. I know this is a really crucial part of your learning, so you're welcome.
Actually 3D, and the flat appearance is just an artifact of the schematic. So this is a unit quaternion with a vector part and a real part. Let's think back to complex numbers for a moment. To specify a complex number z on the unit circle that makes some angle theta with the horizontal, you can write z equals cosine theta plus I sine theta. Increasing theta will rotate a point around the circle passing through 1 and I. But instead of multiplying sine theta by I, we can multiply it by any unit vector, so long as it's orthogonal to the real axis, and we would still get a unit circle. So let's do exactly that. Q equals cosine theta plus sine theta times the vector x times I plus y times j plus z times k. We are multiplying sine theta by the vector part of a quaternion, And in fact, the whole equation describes a single quaternion whose real part is cosine theta, and vector part is sine theta xi plus yj plus dk. Now, instead of making a circle that passes through 1 and I, like complex numbers, we have made a circle that passes through 1 in any arbitrary point on the 3D unit sphere.
Mm.
3D, since there are only 3 components in the vector part of the quaternion that is multiplying sine theta. And since this point in the ijk space is orthogonal to the real axis, we're still forming a unit circle, assuming that x squared plus y squared plus z squared equals 1. Also, this guarantees that the whole quaternion will still have length 1, since cosine squared theta plus sine squared theta equals 1 is always true. Now, think back to quaternion multiplication. Multiplying by quaternion q will rotate two circles, the one passing through 1 and the vector xi plus yj plus zk, and the perpendicular circle to that. Multiplying by q conjugate will rotate both circles in the opposite direction. But like before, if we right multiply by q conjugate instead of left multiplying, we will only negate the rotation direction of the one circle passing through 1 in the vector part.
Hmm.
So if we multiply q conjugate, both opposite rotations passing through 1 in the vector part will cancel out, while the other rotation will be doubled. So the vector which we are
We're back.
rotating
We're back.
about
I
is given
understand
by the
this.
vector part of q, and the vector which we want to rotate is given by v. Much like complex number multiplication, the angle that we want to rotate is given by theta in this expression. But there's a catch. Since we sandwich
There's a
v
catch.
between q and q conjugate and end up doubling the rotation about the vector part of q, we actually end up rotating v by 2 theta degrees.
Oh, I remember
Side
this. Yeah, in another video, they're like, "Hey, we have to divide by two," and it was arbitrary. But now I get it because when you add q and q is a q conjugate. I think that's the word. Sorry, I've been saying q inverse, right? Q conjugate. Then you're actually rotating double the amount because they're both spinning. And it's because, oh, that's what the difference between left and right multiplication is. Because if you multiply the left versus right depends on the rotation it's going by, or which direction it rotates. So if you put it on the left and right, doing I and negative I, then they're both going to rotate in the same way, which I kind of picked up, but I don't think I really understood until now. Everything else I don't get.
The effect of this doubling of the angles is that there are two ways to specify any orientation in 3D space using quaternions. If q rotates v to a particular orientation, then minus q will also rotate v to that orientation. This property is especially useful for animations when you want to interpolate between two orientations. It allows the programmer to choose whether to take the long path or short path to the new orientation. The fact that quaternions behave so nicely when interpolating is a major reason that they're often preferred over Euler angles in 3D graphics, which are prone to gimbal lock when two axes align during
This
interpolation.
is what I was talking about.
Hey, are you listening?
Inspired by Quaternion multiplication, I present the super double four-dimensional flip of the century.
You just go crazy. Oh,
Try
oh,
negating
broke
the
his neck. It's
quaternions. A
over.
front flip might be
His math
easier.
career is over. You stupid. All right, it's over. Okay, so okay, honest review. Going through this, I understood I understood what they were talking about and like the logic. Let's recap. So a quaternion is has four parts. It's a four-dimensional way of describing rotation. There's your real part, and then there's the I, J, and K, which represents different axes. That's great. I understood kind of what they were talking about of rotation, and then maybe maybe going back, like again, it was this Johnsky, right? Because you like when you multiply, I think it was talking about multiplying these imaginary numbers together and giving some like defining inequality or defining these equalities, give you these properties. That makes sense. I think I was kind of lost at
But
not this part. This part
with
makes
the
sense. I think it was like kind of right here when he started mixing them all together and then relating them and then putting them together. I got some of it, but I don't understand fully. This one just that just lost me. I'm not gonna lie. I didn't show it because I don't want to stop the video again. But I think I'm going to need some more time on this one. It's great. I definitely have a better basis of what quaternions are, and I'm going to feel more comfortable. If you guys already get this, you're so much smarter than me, and kudos to you. I don't know why you're watching this, but yeah, I'm going to need some more time on this. But to my geniuses out there, thanks for watching. I'm going to suffer again.